is our last bout with derivatives. Okay, 6, 7, 8 next semester will take us into integration.
No, fresh start.
Well, you still have derivatives. You're always still going to have derivatives, just like limits are still there. Okay, but we'll take a break. We won't do as much with derivatives because we'll focus on integration. Now, here's the deal. Integration is very much based on derivatives. Okay. We learn integration rules, but integration is pretty much doing the opposite of derivative. Another name for integration is finding the antiderivative. So we'll talk about that all in January.
Which one do you think is easier?
I personally think derivatives are easier. Well, and it's, I don't know, I feel like they're easier, I think, just because we do them first. We get those rules all set. And then sometimes when you throw in the integration rules, it muddles it in our brain a little bit for a bit. So I prefer just the going straight forward.
What chapter is the hardest?
I don't know. I don't have an answer for that one. They all have their own thing. So.
Hopefully I'll get right.
Okay. So lesson 1 in unit 5 is mean value theorem. So we have several theorems throughout the year. I'm not even sure which ones we've talked about and haven't talked about yet, but mean value theorem is another one to talk about. Okay, so we're going to look at some examples on this first page here that are going to help us to understand the mean value theorem and go from there. I'm on the right page of my notes. So, kind of a discovery here. We're going to use these graphs and the questions below to explore conclusions to the mean value theorem. So down below are the directions. And number 1, it says to draw the secant lines for each figure on the given intervals. Now, do you remember what a secant line is?
Does it intersect it?
It's going to intersect.
At what point?
Not one, but at 2 points. So if it's a tangent line, it just touches the curve once. If it's a secant, it's going to cross through it twice. And so basically we're looking at the 2 points they already have. So draw the secant lines for each figure on the given intervals. Now, you guys can always grab rulers if you want. I can't use a ruler on the big Q. But in figure 1, you have a point. You have a point. What's the secant line going to do? It's going to go through them. Now, it's going to cross through the curve in another spot also then. But your secant line is going to be doing that. So this is my secant line if you want to label it. Let's do the same thing on figure 2. We're going to cross through the 2 points there. And this looks so much neater in my notes because I can use a ruler in my notes. This is my secant line. Okay, it's crossing through 2 points. Have you looked at figure 3 yet?
Oh man, I don't know.
Figure 3 has 3 official points. We're going to do 2 secant lines is what we're going to think. Yeah. We're going to do 2 secant lines. We're going to do a line here on the left through this left curve that goes through there. And then we're going to use the same middle point and we're going to do a line through there. Does that make sense?
Yeah. Missed.
Did you say you missed?
I missed, yeah.
Hey, that's why I said you guys can use a ruler. If I could use a ruler on the bin Q, I would in a heartbeat because that's why you see me erase so many times. And on figure 4, you see your secant line here. This one's hard for me to draw. Ooh, that's not bad. I'll take it. Okay, we got our secant lines, yes? Draw the secant lines for each figure on the given intervals. Good?
Yeah.
Okay. Step 2. Are there any points on the graph of each function where the tangent line to the graph appears to be parallel to the secant line you've drawn? Draw a tangent line between endpoints of the given interval, if possible. Let this point of tangency be called x equals c for each figure. So as we do this, can I draw a tangent line that is tangent to this graph somewhere that is also going to be parallel to our secant line that we've already drawn? So as we look at figure 1, so here's my secant line, yes?
Yeah.
So I need a line at that angle, as I hold that pencil up, that is tangent somewhere.
Does it have to be at the same points?
No.
Oh.
No, it's not going to use those same, it's not going to use the points we drew for the secant
I
line.
thought tangent could only go through once. Touch.
It touches,
Because if you would draw one at the top of the slope,
It would go through that.
it would
Okay.
go through the.
so like you guys are seeing like this right here, yes?
Yeah.
And this is, I didn't get mine exactly parallel, did I? But you see the intent here.
Yeah.
Okay, pretend those are parallel lines.
Yeah.
That is one of the lines we're looking for. Okay, that is, and actually, hold on. As I just looked in my notes, I actually stopped it right there in my notes. Now,
That's fine.
I know technically a line keeps going, right? So I mean that argument is valid. With a tangent line, I guess I need to look up an official definition of how, but the tangent line, does it touch this curve at one point?
Yeah.
It does not cross through this point right here. And if this curve didn't go back up, it wouldn't cross through. Okay, so this is tangent at this point here, and I'm going to call this, they said call it C. I'm going to call it C1. Because there's a second tangent line, isn't there? So this is a tangent line. Do we have another spot we can do a tangent line that is parallel to our secant line? Yeah, we can do one down below, I assume. And again, I'm making it more local. And I'm going to call that C2. And that's why I used C1 earlier, because we've got 2 C points on this one. That's our tangent there. Okay, and we're on step 2 right now. That's all step 2 asks us to do. Just draw tangent lines, if possible. Label the point x equals c for the point of tangency. Okay. What about figure 2?
No, because you can't take the derivative. It sounds it's a sharp angle or whatever. It's a cusp or something.
Okay, good job, guys. So we want to draw the tangent line right there, don't we? Because we see it, we're like, oh, there's a point I could use to make my tangent line. It would be parallel. However, it is a sharp point or a cusp. So it's a no-go. Okay, figure 3. What about this one? Any tangent lines? See one on the left? On top of the curve? Maybe about there? I'm going to label this as a tangent again. Any others on figure 3?
Yeah. Down below.
Down below? Let's see. Yeah. I can visualize it parallel better than I can draw it. Does that make sense?
Yeah.
That's not exactly right, but you get the idea there. So I'm going to have a C1 and a C2 again on this one. And that's my other tangent line. Okay. Figure 4.
Wait. No.
Yes.
Oh yeah, you can on the other
On the
side.
inside.
Okay, I'm on the inside. And again, I know you guys are going to argue it's breaking a rule, but
So, okay.
No, break.
So sometimes you can break the rules.
I guess. It's weird.
No, it's not this one.
something along those lines is where it's supposed to be at. I'm not loving my line here.
Okay, wrong. Just broke the rules.
Okay, and there's my C value, and that is a tangent line. Okay. And this was step 2. Draw a tangent line between the endpoints, if possible. Let this point of tangency be called x equals c. Okay, good?
Yeah.
Step 3, or question 3, whatever you want to call it. For each figure, estimate the value of x equals c where the tangent line is parallel to the secant line, or explain why it's not possible. So in figure 1, we had C1 and C2. I'm going to put them down here. You can put them up there if you want. But what would you say C1 and C2 are? Where do you think C1 is? So C1, what x value is that at about?
Oh. Like 2.5.
Yeah. I have 2.5 in my notes. And I wasn't even looking at my notes when I drew that. I just, ballparking it. What about C2?
C2.
Mine's a little past 7.
7.25.
Yeah. I think the notes say 7.2, which I kind of agree though. 7.25 seems a little more natural to say, doesn't it? So I don't think it matters what you put because we don't do anything with these numbers after this. We're just identifying them. Okay, what about number 2?
Cusp can't do it.
Okay, there was no tangent line, and that's because there was a cusp. Number 3, we had 2 C values. On C1,
2.5. 2 and 0.75.
mine ended up about 3. And again, we're ballparking it, right? If yours is a little over, that doesn't make it wrong. And what's the other one at?
6 somewhere. 7 or 6.
Yeah.
6.5.
Mine ended up at 6, but I could very easily have scooted mine a little bit to the right, I think. Ballpark, right? Remember, this is kind of a discovery, exploration activity here, trying to help us understand. And what about number 4?
I would read at 4.25.
I don't know. I almost feel like mine's touching at 4 and 4.5, and I don't know. In the ballpark there, 4. I heard multiple good answers there. Those are approximates, right? Okay. Ready to talk about number 4?
Yeah.
Which functions are continuous on the given intervals?
1.
So graph 1, which officially Graph 1 is f of x, graph 2 is g of x, graph 3 is h of x, and graph 4 is k of x. So is 1 continuous?
Yes.
Yes, it is. So I'm going to call that actually f of x. If you want to use 1, that's fine. I don't care. Graph 2.
No.
Is it continuous? I'm not asking about differentiable yet.
Yes.
I'm asking about continuous.
Yes.
Continuous is basically, can I draw it in one fell swoop without picking up my pencil?
Yeah.
So yes, G is continuous. And that's a very basic version of continuous, but that's the general I always go back to. What about H? No, that's two pieces, right? There's two pieces. There's a jump discontinuity there, maybe you could call it. That's a no-go. What about K?
Yeah.
It is continuous. Okay, so those are continuous on the given intervals.
So that whether or not there's a dot in the cusp doesn't matter about moving. Like on figure 4, there's a point at the cusp, but there's not a point at the cusp.
And we call them both continuous. Yeah, because they're both still one, I want to use the word continuous graph, but one flowing graph. Sorry, I'm not the art person. Maybe you guys have better words for this, but that's trying to make it basic. Now, which functions are differentiable on the given interval?
And h of x.
Okay.
And
Is f differentiable?
yes. Yes.
Yeah, that looks like a basic polynomial curve. F is a definite. What? Is that what we're doing here?
Uh-oh.
Wait a minute. Well, okay, I'm confused. Okay. What do you guys... On the given interval.
Oh.
My brain is thinking the whole graph,
Between the.
but...
I'm seeing what you're saying.
Yeah, hold on. I mean, continuous, it doesn't change my continuous answer. But it's going to have an issue with it's going to affect differentiability. So, which functions are differentiable on the given intervals? So the interval on this one is from, like you see this dotted line here to this dotted line here. Now, there's no issues on graph F. It's continuous, it's differentiable, no question about it. But it changes things up somewhere else. So, okay, figure 2.
Okay.
No.
From here to here, is it differentiable? No, because the cusp is in that range, yes? Okay, so we're back to that same problem. Figure 3, they actually give us 3 points, don't they?
The first
But,
half is what the second half.
yeah, and I don't know. I don't know what interval they're referring to there. I don't know. It's not going to be because of that. I assume. Yeah, it's not going to be because of that gap right there. I'm not exactly sure how that plays into her intervals, but
If you were just doing the whole graph, could it be?
for one, something has to be continuous to be differentiable. And it's not continuous, so it can't be differentiable.
Everything differential is continuous.
Right. Because remember, yeah,
Everything
if something is differentiable,
is different.
when they tell you in a word problem, this is differentiable, you assume, oh, okay, that means it's continuous. If they tell you it's continuous, well, you still have a question of differentiable. Right.
This,
Okay. What about figure 4?
yes, on the interval.
On the interval. Interval going from what? 1 to 5. That is just
Through cusp.
one curve that we end at the cusp, which means it's really just an endpoint, it's not a cusp. And so, what is this? K is differentiable. Sorry, that's how I knew there was an issue when they have one cusp as differentiable and the other one not. I had to figure out I had to remember what the intervals were. Okay, question 6 is kind of, we've already done it. 5 was which functions are differentiable. 6, which functions are not differentiable. Explain why. So what was our problem with g of x? Yeah. G of x has a cusp at x equals 5. What was our other one that was not differentiable? H. H is not continuous at x equals 5. Come on. H of x is not continuous at x equals 5. Okay? Okay. That leads us into, and I know it doesn't seem like it, but we just drew all these parallel lines, right? Parallel secant lines and parallel tangent lines. So that leads us into what is the mean value theorem? So, mean value theorem. This is one of our theorems to add to our list of theorems. If f is continuous on the closed interval and differentiable on the open interval. So continuous from endpoint to endpoint and differentiable from endpoint to endpoint, but you don't include the endpoints. There exists a number c, so there exists a value in the middle somewhere, such that f prime of c is equal to f of b minus f of a over b minus a. Okay. Look down. Well, okay, so first of all, let me point out, it said continuous and differentiable, right? For this theorem to even apply, we have to know that. Verbally, when they give this piece right here, f prime of c equals f of b minus f of a over b minus a, f prime of c is instantaneous rate of change, or in other words, what we lovingly refer to as IROC, equals average rate of change. What's the right side of this?
AROC.
F of b minus f of a over b minus a. That's AROC. Okay? When we talk IROC, we're talking about the tangent line. When we talk AROC, we're talking about the secant line. And your tangent line and your secant line were parallel the way we were doing this. Okay? So, all those lines we drew here, folks. I guess we're missing A in this lovely little picture here. Let's see, A should be right there, it looks like. Okay, so mean value theorem basically says the slope of this line, the slope of the tangent line right there, is equal to the average rate of change, which basically when we don't have the information at a specific point, we do the average rate of change in that area, right? And so that's using the 2 points, the 2 endpoints there, so A and B, and it's saying that those two are equal. Well, they're equal because they're parallel lines, right? Parallel lines have the same slopes. You learned that back in Algebra 1, and again in Algebra 2, and again in pre-calc. Okay? At some point, I think you're supposed to know it, but I'm still going to remind you. Okay, so that is mean value theorem and what we're going to be working with. Okay? So, Rolle's theorem. Okay? This is a special case of mean value theorem. You sometimes hear it's a sidebar. Okay, it's a sidebar of mean value theorem. Or in other words, it's still mean value theorem, but it's one particular case, so a special case. Okay? You'll notice a lot of this reads the same. Let f be continuous on the closed interval and differentiable on the open interval. So still continuous, still differentiable. Here's the special case. If f of A equals f of B, what do we mean f of A equals f of B? The endpoints of that line are the same, which means it's creating a horizontal secant line. Okay, so if these two endpoints are the same, so basically the y values are the same, then there's at least one number in the interval where f prime of c equals 0. And why is it equal 0? Because if you have a horizontal secant line, parallel tangent line is also going to be horizontal. You're going to have a slope of 0. Party in the hallway? Okay. If these conditions hold true, then there's at least one number in between A and B that the tangent line is horizontal. Have I made that make sense at least a little bit? Okay, obviously when we go to look at some of the examples and stuff, it'll make more sense, but I have written in mind the slope of the tangent line is 0 here. The slope of the secant line is 0 here. Okay, and when we talk about f of A equals f of B, that's basically saying like y1 equals y2. Okay, it makes your endpoints have to have the same y's, they have to be equal. So whatever you need to write down. Okay, important note, both Rolle's theorem and the mean value theorem guarantee at least one value strictly on the open interval. So these are existence theorems, I guess you could say. They guarantee something will exist. Now, two questions here. What's the difference in conditions between the MVT and Rolle's theorem? Yeah, Rolle's theorem, it sets it up where your secant line has to have a slope of 0, right? So Rolle's has a secant line whose slope is 0. That's not required in MVT. So Rolle's has a secant line with slope equals 0. Okay. Now, what does Rolle's theorem tell you must exist on a given interval? And it doesn't explicitly say it. Okay, it says there's a number in between A and B where the derivative equals 0. What's always going to happen here when the derivative equals 0? So what's our mathematical word for a peak?
Max.
A max or a min. Okay. Hey, I knew what you meant by peak. I was just looking for min and max. Or extrema.
Yeah.
There's a good mathematical word there too. Okay, so an extrema must exist. So I'm going to say an extrema, and I'm going to put in parentheses, min/max must exist. And you could say because, what do I want to say? Slope is 0. Okay? Anytime you have a slope of 0, that's going to be a min or a max on a graph.
Are we going to draw one of these?
Huh?
We're going to draw one of these.
We're going to draw on them, yeah.
Oh boy.
Okay. Example 1 here. Use the table of values below to sketch the differentiable continuous function on the grid. We're going to have to all take time to do this. Okay?
Gotcha.
Before we can really answer A and B and C and D, I don't know why she didn't just provide the graph, but she didn't. So, we can do it. 0, 1. You guys know what you're doing here without me? We're going to put a point at 0, 1. Then I'm going to put a point at 2, 4. Can I quit talking?
Oh wait, oh, then.
Okay. I would ask that you connect these points in a flowing, curvy graph. In other words, not a pointy graph, but am I making sense there?
Yeah.
Yeah. Let's see.
Okay. Okay, let's see how many of these questions we can get through now. A, find the average rate of change of g of x on the interval 2 to 9. We don't even need the graph for the part A, if you ask me.
11 minus 4 over 9 minus 2.
Yep. So we're being asked to find A rock, which is slope of the secant line. I'm going to write mine out first of all as f of 9 minus f of 2 over 9 minus 2. But I watched your values and you guys had it right. 11 minus 4 over 9 minus 2. So 7 over 7, which is 1.
Yep. Sorry.
All good over there?
Yeah.
Okay. Okay. B is g prime of 6 equal to the slope of the secant line from part A, and justify.
So from 2 to 9.
So is g prime of 6 equal to the slope from part A? What was part A? 1. So we're asking, is g prime of 6 equal to 1?
Yeah.
Because the change line would just be the same line as.
So where is 6? 6 is this right there, yes? Now, we're looking for the slope of the tangent line.
Oh.
Yeah. So you have to touch that.
I think so.
But, okay, the slope of the tangent line, it just has to touch this right here, and this is really hard to draw. Does it have to go through anything else here? No. And will it necessarily go through anything else? It really shouldn't if it's a true tangent line, right? If it's a tangent line, it's only going to touch that point right there. I don't know if that does it justice or not, but it's going to touch that point right there. So we know it has to go through what? It has to go through 612.
Well, we can look at the.
What's another point that it goes through,
We
maybe?
can look at the chart too, because it has 7. Right? Because the ratio is 1 to 1.
Right, but we're not going through. I don't know. Do you guys see where this is going?
A little bit.
I mean, from
Kind of looks like it.
2 to 9. See what? Okay, let's make this more visible this way. We did A rock from 2 to 9, yes?
Yeah.
So from this point to this point.
Oh, that's the secret.
They have to be compared.
Are they going to be equal? I should have just drawn that to begin with, I guess. I was trying to process the best way to go through it too. But they're not going to be equal, okay? I have on mine, what did I use? I don't know. I have values down, but I think it's just easier to look and see that the slope of the secant line does not equal the slope of the tangent line. Fair enough?
Yeah.
Okay, so is it, I'm going to say no. Slope of the secant does not equal slope of the tangent. Okay. We could also say what? They are not parallel. And the better calculus explanation is the fact that the slope of the secant and the slope of the tangent are not the same. But that gives you some ideas. Okay, C. Do I have time? Ugh. I don't know. Does Rolle's theorem apply on the interval 4 to 9? Explain why or why not.
No. 4 to 9?
Oh, wait, yeah, that's a different one, isn't it? 4. Whoops. Where's 9?
No, because it's not horizontal.
Yeah. Whoops. So 4 to 9, I can't even get that in drawn right, but it wouldn't be, Rolle's has to be horizontal. Okay? Remind me, we'll talk about that Monday and write that in.
Okay.
Hopefully, Caitlin, you do the notes this weekend, otherwise this is going to be a weird place to jump in. So.